Let me start off. Our first talks speaker is Andrea Bianchi, and he's going to talk about tracking magnetic tokens, short MagnID, and please give him a hand. Oh yeah, and co-author is Oakley, who is over there, supporting. Enjoy.
Good morning. So my name is Andrea Bianchi, and I'm presenting today MagnID. That's a collaborative work I did with my colleague Oakley in Korea. Now, we don't look Korean, but yeah, we live in Korea. So most of you knows about the benefits of tangible interaction, right? How to basically manipulate digital content using real objects. And that's great because it really leverages on the physical affordances, so it's really a natural experience for the users. But when we talk about technology, where we are, when we talk about tangible interaction, we are usually here, right? We are in front of a tabletop. We have tokens, we have things that we move around, but these kind of interfaces, though really great, they're also a little bit bulky, sometimes expensive, and they're just big, okay? So you cannot really carry around. So this really hinders users. That's kind of like the main limitation for getting tangible interaction out there. So there have been proposed several systems to try to solve this problem, and I'm just going over some of them. And some of the systems use, for example, visual tracking. So this is like using a couple of cameras. Now you can actually interact with objects on a screen or around the screen. But the problem with this one is that it's still kind of bulky, and because it's based on camera, there are problems with occlusion. There are other systems using capacitive sensors, like those that you have on the screen of the iPad and so on. And that's also great. So what you can do is arranging electrodes, so substantially arranging electrodes on the screen, so to recognize tokens that you actually can move. But what's the problem? It works only on the screen. So you have a very limited space, and you end up basically consuming all the space for putting the tokens on the iPad or on the tablet. So that's why magnets is coming to the rescue. So we all know magnets since when we were kids, right? They're cheap, unpowered, they're small, they're actually great. A magnetic field has two properties. It has a direction and it has a strength. And these two properties can be tracked with modern technology. And I'm particularly referring to magnetometers or compass sensors. And you have them already in your devices. Okay, so it's already there, the technology, and magnets are really cheap. Can we use them? And in fact, has been used a lot of magnets in HCI. This one is pretty much related work that I don't want to go over. You can take a look at the paper. But basically think about using magnets to interact with your mobile devices. You can draw something on your magnets. Or the other way around. You can put sensors on your fingers and interact by having the sensor now on your fingers. Or you can actually put magnets inside of props, like, for example, a pen. But we are more interested about tokens, stuff that you move on the physical world. So in terms of tokens, there have been quite a lot of systems using magnetic tokens. And one of them is the magnetic accessories that I presented at TEI a couple of years ago. And the idea is that you put a magnet inside of an object, and then you can track the strength and the direction of the magnet. So you can move these objects around the device or on the device and recognize where they are. You can track motion. It can be linear motion. It can be circular motion. You can detect location. You can detect orientation. So you can do all these kind of things. But what's the problem? Only one token at a time. There is no way in which you can track more than one token. And that's because the sensor you use just have a single reading. So some other researchers have proposed improvements on this. This is called MagnJets. And the way it works is putting a constraint. You fix the magnetic tokens, you glue them, physically glue them, or attach them to the device. You fix their location. So you can pre-calibrate all the possibilities. So for example, you have sliders you can move, but you calibrate them in advance so you know where they are. So by constraining the location, you can sense multiple magnetic tokens. But then you cannot really move them around. That's a big constraint. perhaps the most flexible of the systems is this one. It's a family of systems called Gaussians, Gauss bricks, Gauss stones. And this is really great. You can track location, so position of the tokens, their ID, their orientation. What's the catch? The hardware. More than 700 sensors on a PCB underneath your device. That's really bulky. Okay, that's very difficult actually to imagine it as a product. So what I'm doing today is trying to show you another system that raised the bar. Can we track multiple magnetic tokens at the same time? And can we do that in a simple way? Can we track what, so the ID, and where in a simple way? So what I'm going to do is I'm going to show you a system, I'm going to show you some applications, and kind of speak about the performance of this system. All right? So a little bit more details. So we want to be able to track multiple tokens. How many? At least 6. Why 6? We just compare with other systems that are out there, like the shiftables. We also want to have multiple locations that are on the device, but also around the device. So all the space has to be tracked. We would like to use just out-of-the-shelf hardware, so the magnetometer you already have on your phone, and then we want to have it simple, because all these projects is actually open source, open hardware, and everybody should be able to actually, go there and try right away. So before I start showing you the project, let me kind of get you with magnetometers 101. Let me get you in shape with that. Let's imagine this case. I have a magnetometer sensor here. I have one magnet here. I have a second magnet here. Now, you wish you would be able to track the location of magnet 1 and magnet 2, but you can't, because the magnetometer will only give you back one single vector. Will basically tell you what is the strength of the magnetic field on the x-axis, y-axis, and the z-axis. So you just get one aggregate value. Okay? You cannot discern. The second thing you can track is the intensity. And we know that the intensity is proportional to distance according to the inverse cubic law. So let's say you have a magnet positioned around the device. You might imagine perhaps having some certain degree of sensing. But this is further away, it will be much less. Okay? So this is basics. I'm just trying to introduce you to the idea. And finally, there is the direction, the north and south pole of the magnet. So imagine I have a magnet pointing north. Maybe I am sensing something like that. But if I flip it, what will I sense? I will sense the opposite. I will sense the negative strength. Okay? So what's the idea? Let's take that magnet and start flipping it. So imagine you have this magnet and you flip it in your hand like this way. What happens? This happens. You make a signal. You make something that looks like a sinusoid. Now, this might not seem very cool, but then you can actually use that. So imagine I have one magnet here spinning 5 times a second, and a little bit further away, another one spinning a little bit faster. And it's like if I have these two sinusoid signals combined, something like this. And what do you do? Well, it looks very complex, but if you look at the frequency domain, what you end up having for each one of your axes, it's 2 clear peaks. One will be at 10 Hertz, and one will be at 5 Hertz. And what is cool about it is that the intensity somehow, it's proportional to the distance. So you can infer where each one of them is. So what did we do? We did a very simple hardware in which you have one magnet, one motor, and you spin it. And you put it in the middle of a token. So you have a couple of batteries. Then you have a very small, tiny pancake-style magnet in the middle. And then you just get it to spin. To control the spinning, we have a variable resistor. And it works like this way. As you can see, I have a screwdriver, and I'm spinning faster or slower to control this frequency. So it's very, very simple. You can do it in a better way. But then when you put it close to the sensor, you're very easily able to identify which one is the one you're getting there. So technology is very simple. We were able to produce several of these tokens, ranging on a frequency between 5 and 50 Hertz. You can do much more. We just did this. They're pretty small, pretty minimal, 3D printed, customizable. That's a pro. And then they're very cheap. It's about $10 to make one, and about 30 minutes fabrication. Okay, so it's kind of very, very easy to do. Then we actually use a sensor out of the shelf, but we connect it to Arduino. Now, you might wonder why we didn't use the one on the mobile device, and that's because you don't really have all the control, all the tuning that you actually would like to have, but it's just a small detail. So we have an Arduino connected to a computer, a commodity magnetometer sampling 100 Hertz, and then a case. That's it. And then we have the software, and the software is divided in two parts to keep it very modular. You have a server that does all the brain stuff, and then you have the apps that run on computers or on tablet. It's up to you. So you read, with the server side, you will read the magnetic field, extract the frequencies, kind of know now what kind of tokens you have, and try to understand its positioning, and then broadcast all of this information using OSC. And then on the other side, you have many different applications that you can create. For example, apps on a tablet devices. You just receive the information using OSC, and then you do the content, and that's it. Okay? So, this is the server side is completely customizable. So we made the interface, and as I said, is open software. The token look like this way on the software. You can activate it. You can actually take a look at details. You can see the signal strength, the frequency, and you can also decide what kind of features you want to get from your token. So we can have 3 different types of tokens that allow 3 different ways of interacting. One of them, we call it an ID token. An ID token basically is just for tracking presence. Is the token there? Is it not? It's a simple threshold. You can go more complex and also detect the location. If you want to have the location, you can also detect the location. So we have position tokens. And also you can have range tokens, parameter tokens. And those are very similar to position tokens, but you need more than one position because you want to slide them and control something that is in a continuous range. See, for these 2 tokens here, we use some machine learning. You can check out the paper for details, but the machine learning basically is done only for these 2 tokens here, for detecting their location. Okay, one more heavy slide, and then we go to the applications. Just to give you a sense of what's going on in terms of technology, imagine you have 2 tokens there. We said before, you get a cumulative value. That's your magnetic reading. You extract the frequency. So by applying a filter, you get a signal like this one. You just do some DSP, digital signal processing. You rectify, and you try to get something representing the strength of that magnetic field. The average is not really complex. And then use that value basically and feed it in a machine learning tool to basically say, okay, the strength of these signals is somehow proportional to the location of this token. And then you broadcast all of this information. All right, so this is what it looks like actually, the interface. So all of this happens behind this interface. So you have all the tokens, and you can choose for each one of them what kind of token you want to have, if you want to have them active, if you don't want to have them active. And then you have a sort of tools all over there to see the raw signal. You know, you have to, if you want to look at the frequency domain, or if you want to calibrate your tokens, you just do one time. That's the interface used to do that. All right, with all of these, we did some applications. So that's the fun part. What can we do with this? And we came up with a set of possible applications using the ID tokens, tracking the presence, tracking the location, and tracking ranges. So I'll show some videos and speak over. So this is tracking the presence. You just put a token on a physical cage, and it appears magically over there on a virtual. So you can put many of those, and when you remove them, they disappear. So you have this nice integration between the physical world and the virtual world. And you just do this in a very, very simple way, right? You just put the magnetic token there, they're flipping different frequencies, and tack, it detects it. So this is pretty much the simplest of the cases. You can go a little bit more fancy, tracking positions as well. So this is the old riddle of a chicken, a fox, and a grain that have to go on the other side of a bridge. There is a farmer that helped them out. So you can control each one of the token and moving them from one side to the other side of the device. And each one of them will be identified, and also the location will be actually correctly estimated. And that's pretty much how it works. Now, the cool thing is it works around the device. The next example is the same idea, but it works also on the device. So this is a learning tool for teaching children languages. You put an animal on a language, and then when you tap, so it's a mix of capacitive and magnet in this case, when you tap the language, it will say elephant in English. And then you put on German, elephant, and so on. And then if you put on other tokens, each one of them will be uniquely distinguished. So now, caballo, I don't speak Spanish, but the actual application as a sound, I removed the sound, but that's pretty much how it works. So you can put as many as you want, and they will be all recognized. Okay? Something else we can do with this. Well, you can track still position, but now you can use them as a sequence of command. So this is a logo-inspired game. It's basically a toy to teach children how to program. You take this token representing action, like make a turn, go straight, and you instruct the turtle how to behave. So in this case, you will say, go straight and make a, well, it's really fast. But I guess you get the idea. You instruct, and then we'll keep looping and do all these actions, and you can get the turtle to draw. So kind of like a cool application. So we have 8 tokens, and you can have a variety of things you actually can do on screen. And finally, we have parameter tokens, which is you have a range. In this case, I have 2 tokens, but you can slide them on a continuous range. One of them is a color, and one of them is the brush size, and you control them when you're drawing. So it's very simple, intuitive, and you basically do bimanual input. You can draw with one end and use the controller with the other one. It's, again, a very simple application. That's my beautiful drawing skills. Yeah, it's on purpose impressionism. But, yeah, I'm going to skip on this. Videos are online, as well as all the source, all the hardware. I just have to print it, basically. So we also did some kind of a characterization of the performance. This is much better explained on the paper. This is boring, so I keep only one slide. But the idea is, how good is this system? So we tried so first of all, there are many factors that impact on the performance. Your hardware, your setup, the distance, the number of tokens that you have. However, if you go for a very simple grid arrangement, we try extensively, but if you go for a very simple grid arrangement, like 6 different locations, you get 99% accuracy, which is good for 6 different locations. The recognition is about 1 second, 2 seconds at most, and then the distance is up to 20, 25 centimeters from the sensors. Future work. Now, the future work is trying to make better hardware. So we start doing smaller tokens. So these are examples of trying to minimize these. Also, we try to use electromagnets. So I'm anticipating questions. So I'm trying to use a solenoid, for example, instead. Now, if you ask why we didn't use this one, is because it gets very bulky, because of the battery that you actually have to carry. The magnet itself is much more powerful, basically, than not using a 9-volt battery and a big solenoid. So in conclusion, today I showed to you how to basically track multiple magnets simultaneously, a system to do that. The design space you have, basically, so applications, and a little bit of characterization of the performance. With this slide, leaving there the summary, reminding you that there is a demo today. I take any question if you have any. Thank you.
Fantastic. Any questions? Over there. Perfect.
Hello. I'm Luc from Leuven, Belgium. You anticipated many of my questions, but I have another one that you did not answer yet. Because now if you play with these objects, you work in a 2-dimensional space on the table. They're flat on the surface. So is it possible to extend the system so that you can work in the 3-dimensional domain and that you can play with the inclination of the elements as well?
Okay, very good question. So the 3D space, it works already, actually. We didn't explore that space, but because you can actually track the X, Y, Z and all of them basically are independent, yes, it's definitely working. So you can actually stack them, and that's no problem. You cannot incline them this way. And the reason is we put the magnet in the center of the token because we want something that is rotation invariant. So if you put it on the other side, you will still get something working, but it is not reliable anymore. So it has to flip this way, basically.
Briggle LSU. It's technically very interesting work. I think, though, my favorite slide is your second-to-last slide for a particular reason. I think there's a lot of concern in the medical community with rare earth magnets and young children. They get into the intestines and sort of do funny things. So leaky supercapacitors could be your friend because the toy industry has taken throwaway supercapacitors so that with your solenoids you can get a lot of energy from a relatively small battery. I was just wondering also, have you looked at ways to make these resilient so that if a child throws it, that the magnets won't get out and they can't eat them? Or
actually, no. But your suggestion is great. I haven't really looked into the electromagnets too much, but as your suggestion, using a supercapacitor would actually probably be very great to go for that way. We didn't try any actual real experiment with children, so I don't know. But yes,
it's
you have a very good point.
Thank you.
Thank you.
Hi, I'm from University of Michigan, and I think it's really interesting technique, and I just want to know, is it possible to mount several sensors on the mobile device to calibrate in a 3D space?
Oh, that's actually also something that we were interested to look at, like using multiple magnetometers. Yeah. Yes, definitely you can do that. We didn't explore that space. I guess it's not going to be just like a plug and play. There must be some stuff to be done, but I'm sure, yes, it would work and probably also extend the surface you can use, not only in 2D, but as you said, in the 3D space. So yes, totally right.
Thank you.
Thank you.
All right, let's thank our speaker again.
Thank you.